Hi, this is Dr. Neff, and this video is about organic chemistry. Organic chemistry is the field of chemistry that focuses on carbon-containing molecules. And you might ask yourself, why do we have an entire branch of chemistry devoted just to carbon? And the reason for that is simple. There's a lot of carbon-based molecules out there. About 50 million carbon-containing compounds are known so far, and over 90% of the new compounds that are discovered or made each year are carbon-based. And there's a lot of carbon in a lot of different areas in our lives. Slides show that. Here I show some examples of fuels that we might use in every day, from charcoal that you would use in a barbecue, oil that you would use for a lot of different things like gasoline, jet fuel, diesel fuel, polymers and plastics that are used in a wide variety of things, including building materials, eyeglasses, tires, just a lot of stuff. And then drugs and medicines, as shown here, are organic molecules. You are carbon-based, so the proteins, the DNA, all kinds of things inside you are carbon-based. Things that you eat and things that we use to preserve foods are carbon-based. And fibers in a lot of our materials like nylon, Kevlar, those are carbon-based. So part of what makes carbon such an interesting molecule is that it can bond to itself in a lot of different forms, and that's known as catenation. And other elements can catenate, but what's unique about carbon is that it can form much longer chains than other catenators and a lot of different structures compared to other catenators. So it can bond to itself in single bonds, and that gives us alkanes. If it bonds to itself with double bonds, we call those alkenes. And carbon-carbon triple bonded molecules are called alkynes. And then the different structural formulas called allotropes of carbon include diamond, which are shown here, which is a three-dimensional structure of carbon where the carbons are tetrahedrally bonded to each other. There's also graphite, which is what's in pencils, and those are sheets of carbon in 6 carbon rings. And then this is a picture of some nanotubes, which are basically graphene layers that are wrapped up into tubes. And then there's also a picture of Buckminster fullerene with something bonded into the side of it. Now I want to go over a little bit about how we name organic compounds. Even though you won't be held responsible for this, you'll see these names a lot as you move on through your major, and so I want to familiarize you with the method that we use. So typically an organic compound has 3 parts to its name: a prefix, a parent part, and a suffix. And the parent, or the basis of the name, tells you how many carbons are in the longest continuous chain. The suffix tells you what family or what the most important functional group is in the molecule. And then the prefix tells you where and what are the substituents that are added to that. So here's a table of some of the names, base names for carbon chains 1 through 10. Methane, ethane, and propane and butane are just historical names, and then from there on out, pentane, hexane, etc., those are following Greek names. Or is it Latin? There's different ways that we can represent organic molecules. The most simplest, that tells us the least information about how the carbons are bonded together, is the molecular formula. So something like C6H12O only tells us that there's 6 carbons, 12 hydrogens, and 1 oxygen present, but it doesn't tell us anything about how they're bonded together. A condensed formula does give us a little bit of information about the bonding arrangement. So in a structure like this, you start out with a carbon atom, and then what is bonded to it follows it in the structure. So for example, CH3 means that you have a carbon with 3 hydrogens bonded to it. And then the next carbon in the name, or in the formula, is also bonded to that carbon. And what gives us the most information about the bonding is the structural formula. So I've gone from the condensed formula above and written it into a structural formula. So CH3, CH2, 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 CHO is actually hexanal, and that's shown here, where that ending part of the structure is what makes the Al, and that's because it's an aldehyde. And organic chemists also like to use these abbreviated line diagrams where the lines represent the backbone of carbon, in which where any of the two lines join, there's a carbon, and we leave off the hydrogens, but then any other atoms, which we call heteroatoms like oxygen, have to be shown in the structure. So if this is just the above molecule, the hexanal in a line diagram. So if I kind of fill that in, there's a carbon there, there, and so on. And then every carbon has to have 4 bonds. So each of those carbons, I can put dashes to represent the bonds to hydrogen. And then we have the oxygen on the end of the chain. So the next thing I want to talk about is isomers, which are molecules with the same molecular formulas. So that means they have the same number of each type of atoms, but they have different arrangements of those atoms. And there's different types of isomers that we can talk about. So one would be skeletal or structural isomers, where the carbon backbone or the skeleton is a different length. So these two molecules, pentane or 1-methylbutane, those are examples of a skeletal isomer where the pentane has a 5-carbon backbone and the methylbutane, the longest backbone, is 4 carbons. Positional isomers, which differ in the position of a non-carbon group or a double or a triple bond. So if I take a pentene, a 5-carbon chain, I can put the double bond between these 2 carbons, or I can move it to be between those 2 carbons. Or I could take a chlorine that's attached to my backbone and move it to different carbons on that backbone. And we can also have functional isomers, which in this case the type of molecule or the functional group is different. So in the examples I've shown here, this first one has an alkyne in it and 6 carbons. This other molecule still has the 6 carbons, so the backbone is the same, but it's a different functional class because now it's got double bonded carbons, so it's an alkene rather than an alkyne. And then geometric isomers are where the atoms or groups display different orientations around a double bond or a ring. And so we have cis-trans isomers as shown here, where the 2 CH3 groups are on the same side of the double bond, or trans would be there across the double bond. So before we get into looking at practice problems, another thing I want to cover is functional groups. And these are just different groups that we can add onto our carbon backbone that either add new properties or change existing properties, like solubility, boiling point, and reactivity. And most of the ones that we're going to talk about are oxygen-containing functional groups. And so I've listed some of the ones that you need to know. And starting with that is the alcohol, and that's shown here. This would have a OH group added to the chain, or added to the backbone. So remember, in this kind of line structure, what is not shown here is all of the carbons, or the hydrogens bonded to those carbons, which I can signify with those dashes. So you can see I've got a COH group that makes this a molecule. And those types of molecules get an OL suffix to the name. Next, we can have ketones and aldehydes, which are shown here. So these both contain carbonyl groups, so C double bond O somewhere in the chain. When it's a terminal group, which means that it's on the end of a chain, you have an aldehyde. And that's shown here, where, again, that structural group or functional group is on the end of the carbon chain. These get Al suffixes. And if the C double bond O is somewhere in the middle of the chain, then the molecule is a ketone, as shown here, and those get O and E suffixes. Okay, some more oxygen-containing functional groups are ethers. So these are oxygens that are in the middle of the chain. Esters have a C double bond O functionality in the middle of the molecule. Like the one shown here. And the carboxylic acid has the same functionality, the C double bond O, but now it's an OH because it's at the terminus end of the molecule. It's terminal to the chain. The way we talk about these groups that are in the middle of a chain as opposed to the end of the chain is that they're interior. So I can actually go back and clarify that for the ketone. It's in the middle of the chain, so it's an interior group. A lot of the practice problems we're going to have in this section involves you drawing Lewis structures for organic molecules. And remember that our Lewis structures have to follow all the rules that I discussed in that earlier video. And those include things down here at the bottom of the page, like carbon has to have 4 bonds. Oxygen tends to have 2 bonds and 2 lone pairs, nitrogen 3 bonds and 1 lone pair, and hydrogen only ever has 1 bond. And then the details on formal charge. But let's look at this molecule, C3H6O2, and actually let's draw 2 isomers, or see if we can draw 2 isomers. And whenever you're drawing isomers, really the easiest isomer to start with is the one that has the longest chain equal to the number of carbons in the molecular formula. So that one here would be a C3 backbone. And then again, you're remembering that each carbon has 4 bonds, and oxygen likes to have 2 bonds. So let's put a double bonded oxygen onto this carbon. He needs 1 more bond, so we'll put a hydrogen on him. And then oxygen has the 2 lone pairs. So now both that carbon and that oxygen are happy in terms of the octet rule. We need another oxygen somewhere, so I'll put it on this molecule, or this carbon, but I'll make it an alcohol. And so that carbon now has 2 bonds, so it needs 2 hydrogens. So if I add those in, I've now used 4 of my hydrogens, and I need 2 more, so that means I would put 2 hydrogens on this carbon. So let's just double check that we haven't violated any of the rules that we've gone over. All the carbons just have 4 bonds. The oxygens have 2 bonds like they tend to, and 2 lone pairs, and the hydrogens have just single bonds. And we've got the same number of atoms as we have in the formula. So that's one isomer for that molecular formula. Now another thing to remember is that if one of your isomers has a double bond in it, the other isomers that you draw also need to have a double bond, because that's just conservation of the number of electrons that are in the molecule. So again, if I draw a 3-carbon chain molecule here, but instead of having 1 alcohol, I have 2 alcohols, that takes up 2 of my hydrogens and both my oxygens. So now if I go in and fill in those other 4 hydrogens, there's 2, what's wrong with that molecule? And hopefully you notice that these 2 carbons don't have 4 bonds. So there's something pretty wrong with those 2 molecules, or with those 2 carbons. Try that one again. We've got our 3-carbon backbone, and again I'm going to put 2 alcohol groups, but on separate carbons. And remember I said there needs to be a double bond somewhere in this molecule, so I'm going to put it between those 2 carbons. And then to give that center carbon his 4 bonds, I'll give him a hydrogen. And now this outer, or this end carbon needs 1 more hydrogen, and this one needs 2 more hydrogens. So now I've given everything 4 bonds that wants it. The oxygens have 2 bonds, and I've used up all my hydrogens. So those are both good isomers. Another type of problem you might have to do is converting line diagrams back into condensed formulas and structural formulas, or going from a structural formula and a condensed to a line diagram. So let's go from a line diagram back to the one that shows more detail. So remember, wherever there is a line joined to another line, there's carbons, and at the end of a line there's carbons. So we can just count how many carbons this molecule has. So there's 7 carbons, so I'm going to make that carbon chain, making sure that I remember to put that oxygen into the middle of the chain at carbon 6. And then I fill in my hydrogens. And that's a fine structural formula. And now I convert that into a condensed formula. CH3, CH2, 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 COO, CH3. And again, I have 7 carbons, so this is C7, H15O2. Type of problem would be converting a condensed formula into a line structure. So let's count our carbons first. And you'll notice, okay, that there's 6 carbons. So, and then the carbon number 4 has the double bond of oxygen on it, and the last carbon has an OH on it. So that would correspond to this. Move that over here. I've got my OH on the end carbon. So again, you can see that let's just count again. 1, 2, 3, 4, 5, 6. And so at carbon number 4, I need my double bond of oxygen. And that's my structure. One more type of problem would be identifying oxygen-containing functional groups in molecules. So I've got 2 molecules here. And this first one, let me just show you the structural formula just for practice. And then, so that's got a C double bond O in the interior of the molecule. So this is a ketone. And then this has a C double bond O group also in the interior. So this is an ester. Just for some clarity on the ester, this is what it would look like as a structural formula. That would look like in a condensed formula. Okay, so now you can check out the lab pals and do some practice problems, and thanks for watching the video.